In this video, we're going to talk about increasing and decreasing functions, as well as the first derivative test. The first thing to know before we even get into talking about increasing and decreasing functions is that when you look at a graph of a function, you're going to read it from left to right along the x-axis. So, this function, for example, is decreasing from the origin to whatever this x equals a point is, because all the y values are going down or decreasing. And then as I continue along the x-axis, I notice that all my y values from x equals a to x equals b are the same. So that's what we call constant. So if it's not increasing or decreasing and it's remaining constant, we call it constant. And then from b to whatever that point is, I know that my function is increasing because my y values are going up as my x values are going up. So you can actually test for increasing and decreasing functions using the first derivative, and you're able to do that algebraically because if you have f prime of x and it's greater than 0 for whatever from x equals a to x equals b, if that's positive, then f is going to be increasing. So the original function is increasing. And if the derivative is less than 0 on that same interval, then the original function is decreasing. And if your first derivative is equal to 0, then that's going to mean that your original function is constant on whatever that interval happens to be. So let's check out this example. I have this function f of x here, and I actually have the graph of it. And I could probably, with confidence, tell you where it's increasing and decreasing and constant just by looking at the graph. But I'm actually going to use the first derivative and prove this algebraically, because sometimes I don't have the graph and sometimes I'm asked to do it only algebraically, so being able to do that is really useful. First thing I do here is take the derivative of f of x, so that gives me 3x squared minus 3x. I'm actually going to set it equal to 0 because in our last slide we saw that greater than, less than, or equal to 0, 0 must play a big part here. So I find that x is equal to 0 and 1. That causes my first derivative to be equal to 0. So the next thing I'm going to do is actually set up a number line and test some numbers there to see where algebraically this thing is increasing, decreasing, or constant. So here's what I set up. I set up this number line here, and the first things I put on it are 0 and 1 because that's where x is equal to 0, so that's going to give me a constant point to reference. So what I write above the number line is f prime's behavior. So whether it's going to be greater than or less than or equal to 0, and then that allows me to figure out if it's increasing or decreasing or constant. And then underneath I write x equals. So those are the numbers I'm going to be plugging in and trying. So I need to test a number less than 0, in between 0 and 1, and greater than 1. So I just happened to pick -1, 1/2, or 2. Any of the numbers that fall in these categories will still give you the same result, so don't worry about what number you're plugging in there. So what I do is I test f prime. So for example, f prime of -1 is 6, so that's positive. That means it's going to be increasing from -infinity up until 0. And when I plug in 1/2, because it's between 0 and 1, I get -3/4 when I plug it into f prime. That means that it's less than 0. It's going to be decreasing there. And then when I try 2, which is greater than 1, I get f prime of 2 is equal to 6, positive, so it's increasing after this x value. So now, using this number line, I can actually answer our original question where this function is increasing or decreasing. So f of x is increasing on the x-axis, where we have -infinity to 0, not including 0, because this is what we call a point of inflection, where we change from increasing to decreasing. So you can't really go up or down at that point, so we don't include it. And then it picks back up at x equals 1 and goes up from there to infinity. And it's not going to include 1 for the same reason that the origin is an inflection point, so is this point. So that must mean that f of x is decreasing on the x-axis between 0 and 1. So here are some nice guidelines to finding those intervals on which a function is increasing or decreasing. So first of all, the function has to be continuous on the interval that you're looking at, and you can follow these 3 steps, which are really helpful. So if you locate the critical numbers using the first derivative, you can help determine what numbers you need to test within those intervals, much like we did with that number line. So you use that to determine the signs, positive or negative or 0, where f prime of x exists between those intervals. And then you just really test those things to see if it's increasing or decreasing. So that's, if it's greater than 0, it's going to be increasing, less than 0, it's decreasing. If it's equal to 0, it's constant there, just like we just did in that last example. And you may or may not use or hear the term monotonic. And what that means is that if something is strictly monotonic, so if that's a function that's either increasing the entire interval that you're looking at, or it's decreasing for the entire interval. So a function that's not entirely increasing or entirely decreasing is called not strictly monotonic. Shocking. So here we have the first derivative test, which essentially captures what we've been talking about. So essentially what it says that if you are testing critical numbers on an interval, you can actually help yourself by using that number line test. So essentially, when you have f prime of x and it changes from a negative to a positive, you have a relative minimum at that point. And if it changes from a positive to a negative, you're likely to have a relative maximum at that point. But if you're testing and it's positive on both sides of that critical number, so something like this, or if it's negative on both sides of that number that you're testing, so something like that, it doesn't have a relative minimum or a relative maximum at that C point that you're testing. So now let's use everything that we now know and do a couple examples of this. So let's say I want to find all relative extrema of this function, so 1/2 x minus sine x on this interval. So x exists between 0 and 2 pi. So remember, the first thing I have to do is find the derivative of f of x. So the derivative of f of x is going to be 1/2 minus cosine of x. I isolate cos x to get me 1/2, and so the x values between 0 and 2 pi is going to be pi over 3 and 5 pi over 3. So my next step is to take my number line and plug in those two values here. Now those are going to be equal to 0, which I'll set up there, and I'm going to pick some numbers in between those values that don't quite hit 0 or 2 pi and see what I get. So I chose pi over 4 to be less than pi over 3. I couldn't choose 0 because it doesn't include 0. So I get a negative here, so that means it's decreasing. And then it's going to be constant because pi over 3 gives me 0. And then at pi, it's positive. So if I'm going from decreasing to increasing, that means that constant point, that point that equals 0, is a relative min based on the first derivative test. And then from here, I go from increasing to constant, and I tested 7 pi over 4, because again, I can't do 2 pi because it doesn't include it. So that gives me a negative number. So I go from increasing, constant, to decreasing. This must mean that this value is a relative max. And when I look at the graph of the original function, I see what I have on my number line here. I'm decreasing to a constant point, which is our relative minimum, at x equals pi over 3, and then I'm going to increase until 5 pi over 3, so it's constant there, and then I'm going to decrease after that. So that means I have a relative max at x equals 5 pi over 3. All right, now let's try another example. So let's find the relative extrema of this function here. So first thing I'm going to do is take the derivative, set it equal to 0, set up my number line, all that good stuff, see if we can't find the relative extrema using the first derivative test. All right, so when I take the derivative here, I'm going to need the chain rule. So I end up with a function that looks like this. So immediately I can deduce that x cannot be positive or negative 2 because that would zero out our denominator. And the only x value that's going to make this whole thing 0 is just, I care about the numerator, so 4x equals to 0, that gives me x equals 0. So now when I draw my number line, I have 3 numbers to put up there. So at 0, it's going to equal 0, so that's going to be a constant point. But at negative 2 and at positive 2, it's not going to exist. The derivative won't exist at those points, so it might mean that it comes to a sharp point at negative 2 and positive 2 in some sense. But we can still plug in numbers around those negative 2, 0, and 2 to find out what that f prime behavior is going to be. So when I look at this number line here, I find that my function is going to be decreasing, probably hit a really sharp point here because the first derivative doesn't exist. and then it's going to increase and come to a constant point here and decrease, probably hit a sharp point here, and then increase. So because this goes from decreasing to increasing, we're looking at -2 to be a relative min. Same thing at +2, it's going from decreasing to increasing, that's a relative min. And then at x equals 0, we have increasing to decreasing, so that must mean that's a relative max. And when I look at the graph of this thing, it behaves just as we thought it would. It's going to decrease, come to a sharp point, increase, and then decrease, come to another sharp point, and go back up. So because the y outputs at -2 and +2 are both 0, which mean that they both are equal, we have two relative minimums because they are both the same low point on the y-axis. So I've got two relative mins, and then my output for my relative max at x equals 0 is the cube root of 16. So I have three relative extreme points on this graph. So here we have our last example. Let's find the relative extrema of this function here. So again, going to take the derivative first, set that equal to 0, set up my number line, see what happens from there. So I'm going to rewrite f of x so I can take the derivative using the product rule, and I take the derivative here and I end up with an x in my denominator, so that means that x cannot be 0. I'm going to set my numerator equal to 0, and I'm going to factor the 2 out, so I get x to the 4th minus 1, which I can factor and then factor again. So I can set two of these pieces equal to 0, the x plus 1 and the x minus 1. X squared plus 1 will give me an imaginary root, so I'm not even going to work with those. So I have x can equal 0, and my two zeros are -1 and +1. So let's set up our number line. So here we have our number line with -1, 0, and 1. So I'm going to plug in numbers in between all of these points and see if I can't find the extrema from there. So from here, I pick numbers in between -1, 0, and 1, and I find that my function is going to be decreasing, constant out, and then go increasing, and either there's a sharp point or an asymptote there, and then after 0, it's going to be decreasing, come to a constant point, and then increase again. So almost like two parabolas next to each other. And when I actually graph this thing out, that's what ends up happening, which is great. So I noticed that because my y outputs for -1 and +1 are both 2, that means that they are both the lowest points or the relative minimums for this function, and there's no relative max, which can totally happen. So that's my extrema. And that's going to do it for this video. Thanks for watching.